Now, with the evolution of ultrafine plus and surface geochemistry, the first question you may be asking is, what does the FONS have to do with any of this? And where I put this into the presentation is really at the core of the problem we have in near-surface geochemistry, and it's an ongoing problem. And the FONS pictured here highlights the idiom jumping the shark. And for those that aren't familiar with that term, basically what it relates to is an episode in Happy Days where the ratings were starting to go down, and essentially the producers said, do something outlandish, go over the top. And in this case, the FONS jumped a great white shark in California Bay somewhere, some bay in California. Anyway, the point was the show continued to tank, but because of these outlandish claims, the term jumping the shark arose. And I think that's really applicable to surface geochemistry, because through the early 2000s, we've had these techniques and developments that people have said, we'll work through hundreds of meters of transported cover. And I think it's just unrealistic. And we've kind of jumped the shark in our surface geochemistry. And what I'm proposing today is going back through some of the development of the UltraFine Plus and the science behind it and sort of why that makes sense, but also trying to tailor our expectations around, something that I think is kind of new and exciting, but also understanding that it's not going to work everywhere. Realistically, it's going to work well in perhaps 5 to 25 meters of cover, somewhere in that range. But that still opens up a lot of opportunity for exploration in parts of Australia. And so back in 2007, I think it was, Ravi Anand and his teams, and I was part of that team, started working on mechanisms of metal migration in transported cover. So we started doing the science behind, if you're weathering an ore deposit and you've got sand dunes over the top, how do you detect these metals? What do they look like? How do they move through that profile? And so we did some experimental work both in the field and like this, on field sites and like this, and also in lab experiments, where we weathered ore material and looked at how it mobilized up through the profile. In this case, we buried ore in the bottom of those 2-meter pits and started monitoring them over the surface. Now, what we found, surprisingly, was that within 7 months, we could detect appreciable gold in the surface soils above the buried gold ore. And we could detect appreciable zinc and copper above the buried VMS ore. And it was only in the pits that didn't have free draining holes in it. So what it meant was where after the winter rains, things were percolating away and we were getting evapotranspiration, moving those metals up through the profile. Where things free drained, we didn't get that signature at surface. And in the lab experiments, we also did similar things where we souped up that mechanism of metal transpiration, evapotranspiration up through the profile. We were able to mobilize large quantities of pathfinder and target elements up through our sand column quite quickly. But really what that did was get us thinking about, okay, in cover situations, what sort of signatures should we be looking for? And what are those metals likely to be doing? So if they're moving up through a profile like that, they're going to be pretty charged, they're going to be small, they're going to possibly somewhat soluble. And so what that means is that those materials are going to be binding onto things that absorb those types of ions in the environment. And now in soils and sand dunes like this pictured, those are going to be the clays and iron oxides. And what that means is things that have the biggest surface areas are going to be the most important to collect, get the signature. Now, I've got this picture up of a packed MCG that we don't see much at the moment, is to relate to the soil surface area. So if I had a handful of soil that may be about 10 grams worth, if that material was sand, and dominantly what we find in the back blocks of much of semi-arid Australia, the surface area of that material might be a square metre or two, or a couple of square metres. Now, if that same 10 grams is clays, particularly the shrink swell type clays, surface area of that might be the area of the grass there on the MCG. It's a vast increase in surface area and absorptive capability. So if you've got a weak gold or zinc metal moving through an environment, it's going to bind onto the clays and iron oxides, not your bulk sand. So all we did was take that thinking and refine it into the method. And that's where the UltraFine came about, and it was like developing how do we concentrate up that really fine material and analyze it to the best of our abilities. And so I'm going to show a few results. I'm not going to talk about them too much because really it's all been published and it's out there and accessible for you. So there's a GSWA report on the first project. There's also 2 journal papers that are open access. So you can take your camera and take those QR codes and it'll take you straight to where you can download those papers. But essentially what it said was by concentrating up those ultrafine materials, you can increase your concentrations of pathfinder and target elements by between 150 and 350% because you're not getting diluted by quartz primarily. You can reduce the amount of below detection results, and for gold, our example went from about 70% down to 10%, and in the next generation and where we're taking this project, that's going to be down to probably 1% or even less. I think below detection gold is going to be a thing of the past. The new technique also accounts for soil properties, and I won't talk too much about that today, but you've got a whole lot of more information with the process that you can draw on to understand the differences in your soils. It doesn't have a nugget effect either. So that's a big advantage for gold. And there's other papers that I reference in my reports that can take you to more information. But essentially, you're not getting nuggets of gold, so you're not getting the nugget effect. You're getting something much more reproducible and effective. And really, the science isn't that new. What is new is that we've packaged it up with a commercial partner. So in this case, LabWest is the commercial lab that offers it, and made it very accessible for industry. So it's as if you just drop off your soil samples like you would for any other exploration soil survey. Drop it off, and you go with the UltraFine Plus technique, and that's exactly what you do to get the extra information. And so that's what's really new, and that's a licensed trademark from CSIRO. And here's how it's different. You get your standard suite of elements, and so that's nothing new to anyone, but you get a whole lot more in terms of, you get a few more additional elements now. So we're looking at things like bromine, platinum, and palladium, which I think will have real value for nickel explorers. And on top of that, you get a bunch of soil properties, surface area, pH, conductivity, and you get spectral mineral properties. And this, I think, is where there's a real change being made. Now, that's not new. That was already known, but it's putting it all together where people can get that information very quickly. So this is the typical output from the UltraFine technique. Just to show you a few of those results that I mentioned, that you do concentrate gold. So this is a log scale. So here you see the ultrafine fraction in blue compared to different particle sizes, getting more coarse. And you can see nickel, vast improvement in the ultrafine, those clay-sized particles, and same with copper and lead. And you see this pattern quite often repeated, not just at one site, in this case 260 odd samples, but we see that at a lot of different sites. Because we're just not getting diluted with quartz, primarily. Now, when you compare that to traditional aqua regia, so the UltraFine uses an aqua regia extraction, we tend to get much greater concentrations again. So here's gold compared to traditional aqua regia on a more standard sample. And then here's the 4-acid digest. It doesn't work very well for gold, but it has applicability in other target commodities. But you can still see here that the UltraFine is much greater concentrations quite consistently for a number of elements compared to either of the traditional techniques. And that's 2,000 nearly of the same samples reprocessed. And just to show a couple of exploration examples that have been successful, and you can see this is a fairly new discovery, so I can't put the location on there. But you can see quite strongly in a base metal setting that lead and I think this is the gold, zinc, a lot of these silver all showed up quite strongly and quite elevated around the area of interest, which was the two ore zones related to the stars. And then the one on the right shows the DeGrussa mine, which is obviously a very big deposit, and the outline of the iron, the oxide zone that's been mined, and you can see this was before it was a mine. The response above for gold and copper, which was slightly different and offset and related to the way that the ore and the weathering pattern was working in that setting. So it works quite effectively, but other things also work at the DeGrussa site. And then just another example I like to show, reassaying old results. And here you can see this is Geological Survey of Western Australia's work, where 300 samples were collected at a lot of cost, but only about 18 of them had any detectable gold in it. And so when we took those same samples and they didn't show up the only known mine deposit in the area, you can see with the UltraFine, it does actually pick up that Mount Eureka gold showing, but it also, and this is on 4 kilometre spacing, so it's quite broad, but you can see you've got a lot more information. That's just the gold data. There's a whole multi-element suite to go with it that shows a lot more information. And now, obviously this is quite good and we're seeing a lot of very exciting results, but I'm here to say that this isn't, a perfect, technique. There is, sites where it hasn't worked very effectively. There are areas where we've got some false positives, for example. That's the really interesting science going forward that we're really pushing to try and understand how we interpret those better. And I'll move on to that next. This is where I think the solution with surface geochemistry and geochemistry in general should be going. This is Thomas Kuhn, who termed the phrase the paradigm shift in his 1962 book. And what the paradigm shift refers to is not anything that I've shown you so far. It's more about a completely different way of looking at our results. And so I would argue that over the past decades, we have all worked with multi-element data, maybe a little bit of regolith mapping, and we've said, oh, okay, this is the way we interpret our surface geochem. And we all have been trained to look at this diagram from the right-hand side, and you see that, or one way of looking at it, you might see that and say that looks like a rabbit. This is the Wittgenstein diagram that relates to the paradigm shift. And so that's how we've all been trained. But what I'm trying to say is that we've got all this other information and data and the ability to interpret it better, spatial, geophysics, a whole range that we can bring in together and start looking at our problems from a different perspective. And what I think we'll start doing is looking at from the other side of the diagram and perhaps saying this is a duck instead of a rabbit. And that's where that paradigm shift comes in. It's not just doing something a little bit different, it's seeing it completely differently. And I'm hoping that's where we're going. How I think we'll do that is to be able to leverage bigger data and more interoperable data. We're going to do better at explaining false positives because we've got all this other information we can now draw on, spatial data, but also soil parameters that we haven't worked with before. Then we'll be looking to make decisions using uncertainty. And I'll show an example of that in a minute, but it's not it's something that we're really working towards. And the main game is about generating better targets, maybe a little faster and through cover, certainly. But I think it's generating better quality targets more so that is more important. We will accelerate the process in terms of how you derive your understanding of the site, hopefully. And that'll come through putting your data into landscape context early so that you'll be able to interpret it even if you perhaps don't have a strong regolith geochemistry background. You will be able to get that initial understanding by looking at the way the data comes in and the way we auto-interpret that. So that's blending that machine learning approach, and it's also blending in human expertise. So some of these indices, for example, that people will use will automatically generate those in the process. You'll submit your samples to the lab, tick the box for what you want, and also tick another box. You'll have to put in sort of your locations of your data and say, I want the additional data products. And that will come back in some sort of web platform. And I think it will look like this, where you'll have a CSV file with all your data that you can then take and use in other programs. But what you will also see is Geotiffs and maps that you can scroll through quite quickly to look at your data and how it's been interpreted. And that might be, gold divided by the organic carbon content to account for some of that soil variability. Might be something else, and it also might be an uncertainty map, so that if, for example, the dark blue is the area of high uncertainty, as you can see a couple of dots there, if you had a target in there but you weren't as confident about it, it might inform you to go back and sample more, or it might inform you to walk away but know that you probably didn't assess that as well as perhaps the lower part of that image, in terms of having better certainty of knowledge around it. So that's where I think we're going with this. And I just wanted to sort of wind up the talk showing a few of the examples of the UltraFine Plus. gives out in terms of extra data that we're now starting to interpret. So I've packaged up a few things here. On the left-hand side, you see the ferric oxide abundance versus color saturation. So again, in this setting that we were working in, what we had perceived in the landscape as we were sampling was that upland areas or more residual type settings tended to have more hematite. They tended to have more reddish soils. So we're using that to interpret where we were in the landscape. So we're getting that information out of the geochemistry as well. So even if you didn't have good field notes, you could pick it up. What we also noted was that most of the samples that had elevated concentrations, and these dots are colored by regolith types, and I won't show that example about how that fits in, but they're also colored by size from pathfinder elements. So the bigger dots are the more interesting samples for exploration. What you see is there's a trend in this that sits up above the line. So those more hematite type soils tend to have that interesting, and this is, I think, nickel, maybe a couple of other PG type pathfinders in it. But what might be interesting targets are these ones that sit way off this line. Well, you wouldn't even consider looking at those if you weren't picking up trends like this in your spectral mineralogy. So we still don't know yet what the best approach is in that example, but here we have an idea, and this is another major, looks like to be a major discovery coming on in Australia. The star represents the location of that major discovery, and what you can see is that the spectral mineralogy has picked up, kaolinite, and that's what we often get as the primary mineral, not surprisingly. But we see a well-ordered kaolinite in this setting around the mineralization, which is a bit counterintuitive, but I'm not so hung up on the specifics of what the mineral phases are. It's more where we look for differences. But in the secondary phases, you see a different minor element phase, and this is part of our current project, so it's subject to confidentiality. But you can see that clearly that area has a very distinctive minor mineral phase that is picked up in the ultrafine data, but it's not picked up in the chemistry so much as it is picked up in the spectral mineralogy. So pretty exciting in that space. The other side of it is blending in the machine learning. And so what we've done here is pull in spatial data from a large survey region, and again, quite a few thousand samples in this setting. We've clustered it up and then broken out regolith types, not based on traditional regolith mapping. We've done it based on the spatial data, the surface spatial data. And then what we've done is gone back through and said, well, pull out, and this is a gold exploring exercise, pull out your high percentile gold anomalies by regolith type. Because what would happen in this setting normally is that some of those areas would be suppressed. They'd be thicker cover, perhaps sand dune type materials. Their gold anomalies are only maybe a few ppb, whereas, where you've got a little bit more exposed material, your gold anomalies might be tens of ppb. And so what you would tend to do is focus on those. But in the next plot, what you see is as you break it down by anomalies, you see that this example, and in particular, I'll pay attention to this orange line, the anomalies sit out here in this cluster. That would have been completely overlooked if you weren't interpreting it with the spatial data and trying to break out regolith types and do that. And in this case, we've automated that regolith type. But those gold anomalies would not have been picked up because you would have concentrated on perhaps these dark red ones, which do sit near an ultramafic unit. So, they have greater concentrations, and you can see those on the very right-hand side at the top image. So again, just sort of showing the type of thinking we're going with going forward. And so the current project I'm working on is working in a range of different commodity targets. So we aren't just focusing on gold and copper anymore and zinc. We're branching out into a range of different target commodities. We're operating in a range of different states, except Tasmania at the moment. We don't have a site there, but we do have New Zealand. So perhaps we've got a version of Tasmania in our geochem. The exciting part around New Zealand is we're also getting into sites that may be more representative of other parts of the world, such as Canada, for example, and we are looking to expand out elsewhere. So with that, I think we are approaching a new dawn in exploration geochemistry, and particularly refreshing our approach to new surface geochemistry and reasonable expectations on our exploration through cover. Thank you for your time. If you'd like any more information, it is available in these videos and a project proposal, but please, hopefully, you've got some questions for me.